All right. So we're going to start looking at what's known as the derivative tests. So there's the first derivative test and the second derivative test that we use to figure out different criteria or different pieces of an actual curve. I will say the vast majority of this was designed well before we had calculators. Okay, so a calculator, a graphic calculator, does a lot to make this like almost negligible. However, it's still important to understand the concepts behind it and being able to, like, we're going to do a couple of the problems where I'm going to give you information about it, and then you can like do the sketch out based on what you want to happen, and then we can actually use that to come up with what the equations actually could look like. We're not going to, but you actually can. So it's almost like we can actually go backwards from what we want to happen and then say, okay, these are the equations and stuff that I need to make that happen, which actually is used quite often in computer gaming and programming and things like that, where you're looking at doing boundary cases and stuff like that in certain games. So there is a use case for it. It's just not nearly as critical as it used to be. First thing we talked about last class was the critical number. Those are going to become extremely important. Those are basically all the values of where things change. So we talked about the increasing and decreasing actually before we were talking about what the derivative actually does. So the first derivative, if it's greater than 0, that means my function is increasing over that time because the slope is positive. If it's less than 0, it means it's decreasing in the time because my slope is negative. But really the key is once I get things back to zeros, just like we were doing with polynomials, we can easily figure out directions. So that's why having that 0 case is very important. All right, so let's take this first example. Let's start with an easy one. I want to know where this function is increasing and where this function is decreasing. So that means what's the first thing I have to do for this? Find my derivative. So find my derivative. So that should be my derivative. All right. Set it equal to 0 and find my critical numbers. Oh, yeah. But that is actually one of the numbers that belongs to the work. There is one. No, that's fine. This is fairly out the right. What you do? You're fine. Oh, you can do it. Pull up the 12X. And then look at what you have. Good. So just want to call this. That's it. Good. This factor I talked about. Oh, first one, it's on the 12. Although 12 technically is not going to be the right answer, but you could have still factored it. Yes, it's after. Now you can start to see why the algebra comes back to haunt you again. Any problem you get, you want to get it to a quadratic. Quadratics are easy to factor. And worst case, if you can't figure out how to factor it, you could always use the quadratic formula. Yes, it's annoying, but it works. If you can't get it to a quadratic, then we need to start looking at other options. My suggestion would be just graph it and see if you can pull out one number, and then you can do synthetic division to pull that out, and then factor your quadratic or use the quadratic formula to find the other answers at that point. But most of the times we're actually not going to be doing polynomials. We're going to be doing more complicated problems. But that's where you want to look at with your polynomials. Try to get it to a quadratic so you can do the methods that are simpler to do. This one, we can get to a quadratic. I'm going to pull out a 12 and an x. I'm left with x squared minus x minus 2. This one, two numbers are multiplied to 2 and add to 1. So I have x minus 2 and x plus 1. The goal is to get it into things that are multiplied, because then I can set each one equal to 0. So 12x equals 0, x minus 2 equals 0, x plus 1 equals 0. So x equals 0, 2, and negative 1. All right. Now we want to figure out where the function is increasing and decreasing. So what we're looking for is, where is the derivative less than 0 or greater than 0? Okay. If it's less than 0, it's negative. If it's greater than 0, it's decreasing. Greater than 0, it's increasing. So really all we're looking for is the derivative positive or negative? Okay, because that's going to give me the thing. That's why splitting it at 0 makes my life so much easier, because all I care about is a positive or negative. So we're going to look at the ranges for each of these. So the first one is going to be negative infinity to negative 1. Then I have -1 to 0, 0 to 2, and 2 to infinity. So those are my ranges. It doesn't matter the number you pick. As long as the number is in that range, that's all that matters. Because the way any kind of these formulas work, when we find the critical numbers, that's always where it's going to change. Or that's where something is going to happen. So by looking at each of the range, everything in that range is going to do the exact same thing. So it doesn't make a difference where I pick my numbers. So pick things that are easy to work with, not the end numbers. And again, all we care about is the problem positive or negative. I don't care about what the actual answer is. So when we're looking at this problem here, we're going to look at the 12x minus x minus 2 and x plus 1. All I care about is it positive or negative? So pick a number in this first one. Let's do -2. Wait, I'll just change my color. -1/2, 1, and 5. Okay. Again, doesn't make the difference the numbers. So if I plug in -2, my first one is going to be negative, negative, negative. So that means this is going to be a positive or a negative at the end, right? Again, I don't care what the number is. So don't worry about plugging the numbers into a calculator to find the actual answer. All you care about is it positive or negative. So the first one, 12 times anything negative is going to give me a negative. -2, negative, -2, that's easy. It's going to be a negative. -2 is bigger than 1. That's going to be a negative. So my answer is negative. So in that case, this means this is decreasing. Now let's look at the -1/2. Well, the 12 is going to be, that's going to be negative still. That's still going to be negative. But the one's bigger, so it's going to be positive. So that means that is positive at the end. Does that make sense? How we're doing it? As much as I said, we have all this technology and computers and calculators and everything else. Remember, this was designed before calculators. They didn't want to have to come up with numbers. They were looking at ways to be able to do these graphs and figure out what the answers are without having to do a bunch of calculations, because that allowed them to do it faster. If it's positive, that would mean it is increasing. 1. Okay, well, that's going to be a positive. 1's less than -2, so that's going to be a negative. And that's a positive, so that's going to be a negative. So this one is decreasing. 5. Positive. 5 is greater than 2, so that's a positive, and that's a positive. So that's positive. Increasing. Okay? That's all you're doing to determine if something is increasing or decreasing. That's the reason we're factoring it. We're factoring it to find our critical numbers, but also to easily figure out where it's positive and negative. Okay? That part makes sense? Okay. First derivative test. There, like, what the heck is that? If the derivative changes from positive to negative, then that means it's a local maximum because it's increasing into it, decreasing out of it. That means it's a maximum. If it's changing from negative to positive, that would be a minimum. It's decreasing in, increasing out. That's going to be a minimum. If it doesn't change, if it's positive on both sides or negative on both sides, it doesn't have a maximum or a minimum there. Okay. So only the times where it changes does it give me a maximum or a minimum. If it doesn't change, it is not a maximum or a minimum. Something else is going on there. So what you don't want to get into the habit of doing is doing a couple of them and going, okay, increasing, decreasing, increasing, decreasing, increase. Like, just figure out the pattern and do it. Because that is not always going to be the case. They don't always switch. And we actually saw one of those last class, where it was decreasing into 2 spots and increasing into 2 spots because the value didn't exist. They went to infinity at those places. So if we look at the one we just did, we can now determine which one is my minimums and maximums. So -1, it's decreasing in and increasing out. So that would be a, at -1 would be a minimum. Or at 0, it's increasing into it and decreasing out of it. So that would be a maximum. 2, it's decreasing into it and increasing out of it. So that would be a minimum. So if we look at the graph, -1 was a minimum, 0 was a maximum, and somewhere way down here, 2 is a minimum. So we have, that's the first derivative test. Yes.
Highest degree of yes.
So the highest degree of a polynomial will tell you the maximum number of terms it can have -1. So in this case, we know there could have been a maximum of 3 terms. It didn't have to be 3 terms. So a perfect example of that would be x to the 3rd. X to the 3rd has 0 terms, even though it could technically have 2 terms. So the degree will tell you the highest number of terms you could possibly have, but not necessarily how many terms or many terms you're going to have. And that only works with polynomials. So, all right, the second derivative test. So the second derivative tells you concavity. So concavity is telling you basically how the curve is going. So we have 3, actually, and the way this problem is set up, we have five critical points. Okay. Each of those critical points, when we looked at, if I gave you the problem, we found the second derivative would make the derivative zero. Concavity tells you how it's curved. So this is concave down. Concave down is where the second derivative is negative. Okay. The easiest way to remember it is if you're frowning, you're negative. You're smiling, you're positive. Concave down is a frown. Concave up is a smile. Easiest way to remember it. That's where the critical points are. It's never going to actually equal zero. That's the break point between them. Now, just like when we were doing the first derivative test, you can have a situation where it actually doesn't change. Those are both concave up. So that point right there in the middle there is a critical value, but the concavity doesn't change in that situation. That is possible. Just like in the first derivative test, you can have increasing and then increasing. It just doesn't change direction at that point. Okay. Oh, do I put it here? I do. All right. So looking at the second derivative test, how can we use this one to determine if a point is going to be a minimum or a maximum?
Because concave down is normally look like a min. And the opposite for concave.
Almost. You have it backwards. Concave down is always going to give you a maximum. Because the top, the peak, is your maximum. Concave up will always give you a minimum. So if the value of the first derivative is within the range of the concavity, either down or up, it will tell you if it's going to be a minimum or a maximum on that graph. Yes.
What about the interval? Or, oh wait, never mind. I didn't realize what they were. Sorry, between.
D and P, these two?
My bad. I thought this was.
You're fine.
But,
So in this case, if this was my graph, we would have actually had three. Let me actually do this in a different color so you can see. We would have had a critical zero at that point and at that point. Probably wouldn't have had one in there because it doesn't seem to like actually peak at anything. That wouldn't have been a critical number on the first derivative. So, but I probably would have had one there, and that's in that range. That one would have been zero, but what I would have been able to tell is that they don't change. So I don't know, something crazy was going on there, and then we could look at it a different way. So the first derivative test and the second derivative test, which is what this is right here, so you can write this down now, gives you that extra piece of information. It's not always going to necessarily solve every possible problem, but you can use a combination of the two to find them all. Okay. So if the first derivative is zero and the second derivative is positive, then that is a local minimum. If the first derivative is zero and the second derivative is negative, that is a local maximum. Because that's concave up and that's concave down. All right. Let's do this one. First step is what? Find my first derivative. All right, so now I have to find my what? My critical values. So where is 1 plus cosine of x equal to 0?
And you had last year with some flies, if you memorize your circle.
Where's cosine negative? Start there. Which one of the letters is cosine? X or Y? Cosine is X. So that means cosine is negative in what? The second quarter and the third quarter. Okay, good. So now if we look at just the first quarter, because that's typically what people remember, you can remember. Cosine starts off at 1 and goes to 0, right? So if we want to look at it, so the next one would be square root of 3 over 2, square root of 2 over 2, and then square root of 1 over 2. Or 1 over 2. So that right there is pi over 3. So, but that's the first quarter. I want second and the fourth quarter, or second and the third quartile. So the second quartile one in that spot would be 2 pi over 3. And then in the fourth quadrant, or the third, I keep wanting to say fourth quadrant, and the third quadrant, it would be 4 pi over 3. So my answer is 2 pi over 3 and 4 pi over 3. The easiest way to remember this, your first quadrant, depending on how you actually set this up. That's right. Always do in groups of 4. So it's square root of 3, square root of 1. Square root of 2, square root of 2. Square root of 1, square root of 3. Top two numbers always have to add to 4. And it just goes around. And then it's pi over 6, pi over 4, and pi over 3. That's all you actually need to remember. You just need to remember that first quartile, or the first quadrant. Sorry, teaching statistics, we're using quartile. First quadrant. And then you can just use that to go around the circle because you just need to know what's positive, what's negative. Okay. All right, so we have my two answers. And since this one says it's only between 0 and 2 pi, you do not need to have to worry about going further than that. All right, so now the question is we need to use those to figure out what's a minimum or a maximum, right? Okay, so we have so from 0 to 2 pi over 3, 2 pi over 3 to 4 pi over 3, and 4 pi over 3 to 2 pi. And we have 1 plus 2 cosine of x. So the key is this going to be greater than 1? So in this situation, cosine is always going to be what? Up to 2 pi over 3. Actually, I take that back. Great. Okay, never mind. Yes. But the question is it going to be less than the 1 or higher than the 1? Because remember, at this point right here, what happened to these? These were all the negative 1/2, right? So at negative 1/2, this is going to be 0. Before that point, a lot of it, cosine is going to be positive, correct? And again, it's all one thing. We don't have to worry about it. Like in the first, this encompasses the first quadrant. And I know in the first quadrant, cosine's positive. So I know that that's going to be positive. Because up to the 2 pi over 3 is not going to give me enough to make that bigger than 1. Okay? In this area down here, from 2 pi over 3 to 4 pi over 3, cosine's always negative, right? And I know it's going to be bigger than, when I multiply by 2, it's going to be bigger than 1. So that's going to be negative. You could easily just plug a number into your calculator and get the number 2. That is an extremely, that is a very possible situation. Fourth quadrant. Cosine positive or negative? Fourth quadrant, it's only 1. It's going to be positive, always positive. So that means that has to be positive. Is in the third quadrant, correct. But remember, that entire range has to do the same thing because it only changes direction at those 2 points. So since I know in that entire range, the fourth quadrant's in there, that little piece that's in the third quadrant is going to do the same thing that the fourth quadrant's going to do. It's still going to be positive. So that means it is increasing, decreasing, increasing. So 2 pi over 3 will be a max, and 4 pi over 3 will be a minimum. In this situation, finding my second derivative to help me wouldn't be useful. Because even doing the second derivative, it's not going to simplify the problem down anymore. It's still going to end up being -2 cosine x. And I still have to do some calculations and stuff with that. So. Because sometimes the first derivative is just not that easy to break down. So using the second derivative makes it a little bit easier sometimes. So it all depends on what the function that you have is, and is doing the second derivative going to make it a simpler problem to work with. So that's why both the tests, that's why it's not like the first test, like they're both are giving you the exact same pieces of information. It's just a matter of which one's easier to work with in that situation. Now, the second derivative does tell me where concavity is. So if it's specifically asking you for concavity, you have to do the second derivative to tell me where it's concave up and concave down. So this question technically asks what the minimum and maximum values are. So they want you to plug those back into the original problem. I'm going to suspect that everybody in here can type that into a calculator and get the answer. So I'm not overly worried about that. All right. Let's do this one. I'm going to have you do this one in a minute. So I'll do this one with you, and then I'm going to give you one to do. All right. So let's do the first one in blue. So it tells me my first derivative is greater than 0, negative infinity to 1, and less than 0 from 1 to infinity. So what piece of information does that give me? It's a maximum of what? Okay, so somewhere on 1 is going to be a maximum, right? So it doesn't make a difference. It doesn't tell me. So I know that's a max, and I know on this side it's going down, and on this side it's coming up, right? I don't know where it's going up to that point, but that's what the first one tells me. Correct? Yeah. The next one, great. All right. So the next one, it tells me that it is the second derivative is greater than 0 from negative infinity to -2, and from 2 to infinity. So I know somewhere at 2, and since it's increasing to that point, right? -2 is going to have to be below that point, correct? So we'll put it there. And then there's also something happening at +2. So we'll put that there. So greater than 0 means what?
It has a minimum.
So yes, it's going to have a minimum, and it's also going to be concave up. Okay, so it's going to be concave up over here. Between these two, it's going to be concave down, right? And then over here, it's going to be concave up. And I actually probably should write those lower. So concave up to here, concave down there, and concave up there. Right? Yeah. Limit as x goes to negative infinity is -2. What does that tell me? Yes, I have an asymptote. So going this way, I have an asymptote at y equals -2, right? And what about the other side? Going to infinity, I have an asymptote at what? At 0. So I have an asymptote over here, which means this point can't be down there. Which means that point has to be up there somewhere. Does that make sense? Okay. So do we have enough information to sketch my graph? So I know it's got to get close to this, right? It's got to go up through there, and then it's going to curve down through there, and then curve that way. There's my graph. So this point right there is the switch between concave up and concave down. That point right there is the switch between concave up there and concave down. Or sorry, concave down and concave up. Get it backwards. And my max is there. I was a little off drawing my point, but so that meets all the criteria. Okay. Your turn.
Thank you, yeah. Yeah, I don't think they actually tell you specifically where they need it from. So you can kind of. I was like in the last one, I'm like, all right, I'm just gonna look for here, and I'm like, oh wait, I have to look it up because this yelled at me. And you don't necessarily have to go in the order that it's listed. either. So like you can use the other pieces to like, okay, well, I know this means this. Use that to help figure out where some of this stuff goes.
I would start with that. And then use those next.
It is. So So. Or possibly ask. Yes. So different. That's the thing. Good. So we have that. That's good. So let's get up. That's good. Because that's a minimum right now. These are like puzzles. These are literally like, look, what does this give? What does this piece give me? What does this piece give me?
I got thrown off when you said that. Or, like, you said that was- I was second. Oh, doesn't tell you.
All right, so let's look at it. So I know I have it's at 3. I don't really care where it is. It doesn't make much difference. So I know I have a asymptote there, right? So I know something's happening at 2. I know something's happening at 5. And I know something's happening at 8. Right? Because that's what those other 3 things tell me. So 5 has to do with the first derivative. So that's going to give me some kind of a horizontal asymptote because that means it's 0 at 5. So the question is it a minimum, is it a maximum, or is it just happens to be nothing, which is possible. So let's look at my second derivative where 5 shows up, which is right there. So that one tells me that it's concave up, which means 5 is a minimum. So I'm just going to stick 5 somewhere down here. At 2 and 8, it switches from concave up to concave down. So let's make a point here, and we'll do a point here. So here, crossed over, goes down to that point, goes back up to that point, and goes that way. There you go. So concave down, concave up, concave down. There. It's increasing on this side, which is what that tells me. And that one tells me it's decreasing on this side. So now this one I gave you the equation. But let's sketch it. All right, so I'm in my first derivative and my second derivative. Start there.
That's somebody in it. No, just turn up that message. Just there's a few sections that you should. That's what I got to make sure. Oh, you're fixing that. Yeah. Okay.
Can you check my?
Yeah. You can check. I'm gonna go check the answer. Because I don't remember the second one off the top of my head. Yeah. Watch. Good. First term. So what's the one for us? Because you have to do a change of those. You can't just bring it up. Oh, we don't need to do it. That's. Right, where's my?
Oh,
That's an action on the factor out. Because that would make our lives a little bit easier. Okay, just put that down. Yeah. Good as product rule. Oh, try it. What's the worst that happens? Technically, either way it works, but at the end, you're gonna have to make, you're gonna make it a practical. All right, let's see. So first derivative. I'm gonna make u 1 over x. So u prime, actually. Is -1 or 1 over x squared. So it ends up being -1 over x squared e to the 1 over x. Or e to the 1 over x over x squared. So that's the first derivative. Second derivative, we can do this as a quotient rule. The nice thing is I already know the derivative of the top because I just did it. So the numerator is e to the 1 over x squared. Oh yeah, I forgot the negative sign. Yes. And my denominator derivative is 2x. So we have
Numerator. I'm just gonna write that as x negative 2. I need more room. Hold on. Brain's failing me. So those two cancel out. I get negative e to the 1 over x minus 2x e to the 1 over x over x to the 4th. I'm missing a negative sign. Where am I missing a negative sign? Oh, because there was a negative out in the whole front of the whole thing. That's why. Okay. Which changes those to positives. I'm like, wait, I'm missing a negative sign. So the second derivative is e to the 1 over x times 1 plus 2x over x to the 4th. That's the second derivative. So first derivative, second derivative, and original problem. Okay. So now, what's all this stuff give? So let's look at the original problem and see if we can figure out what happens as it's going to infinity. We'll look at the limits of with the original problem. So the limit as x goes to infinity of f of x is what? So as x goes to infinity, this is going to go to 0, right? So what's e to the 0? 1. And then the limit as x goes to negative infinity of e to the 1 over x is. So all that's going to do is basically just put it in the denominator, but it's still going to go to 1, right? And it's 1 over 1, which is still 1. Okay, so I have my asymptotes at 1. I know that much. So let's look at the first derivative now. So that's all that. So let's look at this now. What is the zeros? Can the top ever be 0? No, because e is never going to go to 0, right? So the top will never be 0. So it can never equal 0. When does the bottom equal 0? At 0, right? And so it doesn't exist, but that's still a critical number. Okay, so I have at x equals 0, f prime of x does not exist. So what happens when it's less than 0? So what happens as the derivative is less than 0? So the top will always be what? If I'm going negative, the top is always going to end up being negative, right? Because e to whatever is always going to be a positive number, correct? So that means that whole top piece there is going to stay negative because it's negative that. And the bottom is going to be anything squared is always positive, correct? So the bottom will always be positive. So when I'm going to be less than 0, I know that my it is decreasing. And when f prime of x is greater than 0, it is doing what? It is also decreasing. So if it's decreasing to 0 and decreasing after 0, that means I do not have a minimum or a maximum in 0, correct? Okay, what's happening at 0 in my original problem?
It's closer to one.
It doesn't exist, right? Because it's 1 over 0. So f of 0 does not exist. So that's helpful. Because that means I probably have I have some kind of vertical asymptote there at that point. Okay. So we have that information. Now let's look at the second derivative stuff. So where is this going to be 0? So the bottom is at 0, right? So I have x equals 0, because that's going to make the bottom 0. So f prime double prime does not exist, right? At 0 still. Do I have another point? So this can never be 0. That one's the x equals 0. When does this become 0? At negative 1/2.
That whole-
No. So holes is removable discontinuities. So that means that the limit would be going to that point, but I could factor something out to clean it up and still know where that point exists. So in this case, my 0 is not going to be a hole because there's nothing I can pull out of it. It actually ends up being an asymptote. And we can look at the limit. We can look at the limit of this going from the left and as the right, and you'll see where it's, because as the left, this is going to get infinitely. So if we're coming from the positive side, that one gets infinitely large. So because the denominator gets infinitely small, which means this goes to positive infinity. From the other side, it actually goes to basically 0, because that's going to 0 and that's going to 0. All right, so what's happening from negative infinity to negative 1/2? Is it negative or positive? So that's going to be negative, right? That'll always be positive. That's always going to be positive. So that means it's less than 0. So that means it's concave down. Negative infinity to 0, or not 0, sorry. Negative 1/2 to 0. So that's positive, and now that's positive. So that means it's greater than 0, so it's concave up. And from 0 to infinity, it's always positive, so that means it's also concave up. Does everybody know where I got all this stuff from? So the only thing we don't know what's happening is at 0, right? Because 0 seems to be kind of screwy. The first derivative doesn't exist. The second derivative doesn't exist. It doesn't change concavity at 0. It's always decreasing to 0. Always decreasing. It's never increasing. So let's see if we can look at the original problem and look at the limit as we're going to 0 and see what's happening. So if we look at the limit as x goes to 0 from the right of e to the 1 over x. So as we're coming in, going down, right, that means the x is getting closer and closer to 0, correct? What's happening to this exponent as the denominator of the fraction is getting closer to 0? It's getting bigger and bigger, right? Think about it, like 1 over 1/2 is 2, 1 over 1/4 is 4, 1 over 1/8, 1 over 1/1,000,000th is 1,000,000, right? So this is going to go up. So that's going to basically go into infinity. Let's see what's happening as it's coming from the other direction. So now we have a negative exponent, correct? So really, this is the same thing as saying 1 over e to the 1 over x. Correct? If the exponent's negative, that means it goes the problem goes in the denominator, right? Yes or no? This is where all that algebra comes back. Okay, so we just determined that that's getting infinitely large, right? So 1 over infinity is what? Huh? Right, basically it goes to 0. So from the left, it's going to 0, and from the right, it's going to infinity. And since I have no desire to graph this out by hand, all right, so here's our graph. So there's my asymptote. It's going to infinity as it's getting closer to 0. It's going to 0 on this side. That's concave up, right? There's no mins or maxes or anything else over there. And this one, when this is 1/2, hold on. At that point right there, it switches concavity. So this is concave down, and that's concave up. But this is actually why looking at this in terms of a graph, like actually understanding what's going on, is important, because if you just looked at this graph, you probably wouldn't have known that something actually different's going on in this spot right here. You probably would have just assumed it's going to 0. But it actually does change direction a little bit. Just slightly. And see how it actually kind of like levels off. It's getting into that point. I think that's enough brain fry for the day.